So, as you know, the first pictures from the James Webb came back this last Tuesday. So this isn't going to be a real polished presentation because I haven't had a lot of time to put it together, but we'll see. It's a $10 billion project. It's only a factor of 10 over budget. And what happened is that they grossly underestimated the complexity of the project. And I think after you see these slides, you'll understand that. And it's either going to be a 5 or 10-year mission, depending on how long the fuel lasts. And we'll talk about the reasons for that.
They're projecting 20 years.
40 years? Huh?
20.
20. Okay, the first one was 5. Then they started talking about 10. Well, I mean, the Mars rover was supposed to go for like a year, and I think it went for like 10 years. So, okay, one of the things is, I need my laser pointer. There we go. If this diagram is basically time along this axis, and this is the universe. The Big Bang, it started out as basically a point, something very, very dense with all the energy and matter coalesced in a very small amount of space. And since that point in time, space has been expanding. And so as you go, the first stars were formed about here, and then the first galaxies. And because this, when you're here on the Earth and you're looking back further away from us, because light has a finite speed, 186,000 miles per second, you're looking back in time. So the Hubble would go back to basically some of the medium-age galaxies. The Webb, we hope, will be able to see some of the first stars forming, because first of all, the energy has to be converted into matter. The matter gets coalesced into stars. The stars form together to form galaxies. And we'll talk a little bit more about that. It also has a goal of looking at the chemical properties of the solar system. And there's a spectrograph in there, and we'll talk a little bit more about that. So why do they call it a space telescope? Well, the reason is that it orbits the sun. Hubble orbits the Earth and is close enough that it can be repaired. In fact, there was a major repair done shortly after it launched. But James Webb is sitting out here about 4 times as far away as the moon. And it orbits the sun like the Earth does. And what happens is the Earth is basically pulling the James Webb along with it. And if there are questions about that, we can talk about more about that. The major components that are here are the mirror. You see the gold mirror here. Then this big shield here is the solar shield. And then the secondary mirror is out here. And then there's a the detectors are back behind the center of the main mirror. And there's spectroscopy imaging, and there's an antenna, of course, so it can communicate with the Earth. So this is a video of the unfolding of the Webb. And the first thing they did was unfold some of the solar panels. And then the heat shield needed to unfold. Now, the heat shield is made out of things that are similar to mylar that are coated with aluminum to be reflective. And then this piece that's unfolding now is a momentum, a device for changing the momentum of the system, because the sun exerts a pressure on the Webb. And the purpose of that is to be able to deflect and change the momentum of the space station and conserve the amount of fuel. At this point, you see the shield being deployed, and the shield consists of five layers. Then the secondary mirror comes out and sits on the end of those arms. And now the side portions of the main mirror unfold to create the whole thing. And they had to do this origami style engineering in order to be able to fit it in the nose cone of a rocket. Because if it was fully deployed, the head of the rocket would have been too large.
How big is it?
The solar shield is about as long as a tennis court. The mirror itself, I believe, is about 20 feet, but I forget the numbers. The heat shield was a major piece of engineering. It's got 5 levels, and because it's in space, it's got a vacuum between the different sheets, which helps to isolate it, of course. And so the first layer will deflect most of the sun and will be the hottest layer. And it'll be running at about 260 degrees Fahrenheit. And the goal is to get the detector that's on the opposite side here to a minus 448 degrees Fahrenheit.
Minus.
So you can see that you've got a 700-degree swing there that you're trying to shield the sun from the sun. So the SPF factor, I've heard various things. One site said it was 1 million and another one said it was 10 million. The point is that it dissipates a lot of heat because the detector that is part of the James Webb, if it was on the Earth, could detect the heat from a bumblebee. All right, so this is the electromagnetic spectrum. The visible portion that we see is enlarged here, and you can see that the Hubble goes down into the near infrared, but it's predominantly in the visible and UV. The James Webb goes further down into the mid-infrared. So if a planet passes in front of a star, like this black dot that's in front of this star, then the light shines through the atmosphere. And by blocking out the sun, they can look at the atmosphere and they can separate the wavelengths of light that come through and detect what chemical compounds are in the atmosphere. And from that, they can detect water, methane, CO2, oxygen, water, and to help determine if there is potential life on planets. So this was one of the first pictures that they showed. And this is the Carina Nebula. It's a star-forming region. And you see this bright rim up here at the top of the nebula? It's being pushed down. You can see the spikes of these stars. By the way, the star spikes come in by virtue of those three prongs that are holding the secondary mirror. It's a distortion, but it only comes from point sources. The distortion does. But these stars are pushing this nebula down, and it acts to do two things. It blows away the nebula, so it inhibits star forming, but it also pushes and compacts it, which makes star formation more likely. So this is a stellar birthplace that happens to be in our galaxy, in the Milky Way. And this protrusion up here on the left-hand side is 7 light years high, to give you a sense of the scale of this. All right, so one of the other goals of the James Webb is to look at the evolution of galaxies and black holes. And if you look at this upper galaxy, you'll see like 2 rays coming down perpendicular to the main body. Those are jets that they think is coming out of a black hole at the center of that galaxy. And this is called Stephan's Quintet. You've all heard of Stephan's Quintet before. Are you aware of that?
No.
It was in A Wonderful, how many of you have seen It's a Wonderful Life? All right, well, people on earth say a prayer, and the angels, Joseph Angel and Senior Angel, hear these prayers, and they show this picture at the beginning of It's a Wonderful Life. I think that's one of the reasons that NASA chose this to be one of the first photos that they did. So there are 5 galaxies in the in Stephan's group, but there are really only 4 because this one is in the foreground. It's just hard to tell that. Now, this was a picture that they took of the southern ring Planetary Nebula, and it's taken with 2 different wavelengths of light. So the one on the left is from the near infrared, and the one on the right is from the mid-infrared. Now, infrared has a very nice property. It goes through dust and clouds and things. So it allows you to see things that you may not be able to see otherwise. So here you can see the star at the center that is obscured, and it looks like it's just one star. Now, we know that this area has gone supernova, that it has blown the gas atmosphere from the sun away from it, because we can see these circles of the gas coming out. If you look in the mid-infrared, you can see that there's a yellow star there, or a reddish star. That reddish star is the one that went supernova. The other star is along for the ride and will probably eventually go supernova. So these layers of gas, what they can do is with their spectrograph, they can come in and look at the chemical makeup of it, and they can see that there is helium, carbon, and oxygen in the gas that's out here. And this is the spectra, one of the first spectra. And what they do is they fit it with a line, and so they're lines of water. This was taken from a planet that was orbiting one of the stars, and it's a Jupiter-like planet. It's not as big as Jupiter, but it's similar to Jupiter. And this spectrograph was taken from a star that is over 1,000 light years away from us. Being able to do chemical analysis on stars and nebula 1,000 light years away just is mind-boggling. And this is the deep space mid-infrared image. And there's a lot going on in this image. But when you see that there's a lot going on here, one thing I want you to realize is that this image is of a section of the sky that's as big as a grain of sand held at arm's length. So they estimate that there's somewhere between 100 billion and 1 trillion stars in the universe. So when somebody asks, is there life out there? My answer is, in my opinion, undoubtedly. Is there intelligent life out there? Is there any here? Okay, if you see the star in the middle that has the spoke pattern, and you look upper right, say about 230, you'll see a galaxy that is white and hazy. That's how you know it's a galaxy and not a star. All right, well, look just beyond it, and you see an orange pattern. That is another galaxy. And that galaxy is so far away that its light has been shifted towards the red region and is only seen in the infrared. Now, you'll notice, you see these lines that are below, say about 7 o'clock on the dial relative to that central star, and some of them down around 6 o'clock. You see those yellow lines? I mean, the reddish lines? Those are all red galaxies that have been distorted by gravitational lensing. That there's so much mass between it, between us and those galaxies, that what happens is the light gets bent around and it acts as a lens to focus it, and actually allows us to see further back in time than we would normally. This is called Einstein lensing because it was first predicted by Einstein in about 1917. The human mind is amazing. And then I thought it might be nice to show you a comparison between Hubble and Webb. And what you can see is, there's just, now a lot of this is because of the mirror. A lot of it is because of the instruments, because you can see in the infrared. But they have to do some jiggling here because they're looking in the infrared. They're not looking at wavelengths that we can see with our eyes. So what they have to do is manipulate the images with a color map to make it so that it corresponds to what it might look like. Because this would all be very reddish. And that was the last image that I saw released. So with that, take any questions? Yeah.
There's some of the color shift because of the speed the galaxies are moving, like Doppler shift stuff.
Yes, that's exactly right. Then what's happening is that space is expanding. We don't understand why it's expanding, but it is. And what that means is that galaxies that are further away from us are accelerating away from us. All right? Accelerating. The universe is not static. And the Doppler shift, have you heard us been on a street corner and have an ambulance go by, and as it's coming towards you, you hear a higher frequency, and as it goes away from you, a lower frequency, or a train for that matter? Then that is the Doppler shift in sound. This is the Doppler shift in light. Very good. Yeah.
Yeah, is it because of the expansion that nothing collides, like something which is set in space doesn't collide with anything else because of the expansion?
Yes. Okay, the question is it due to the expansion of space? And the answer is yes. It's that things are getting further away.
Is there any chance that the telescope will be hit by something?
All right, that's a very good question. Is there a chance the telescope will be hit by something? Well, you remember when I put up the slide about the orbit? That this orbit is what's called in a metastable position. They didn't want to put it in a stable position that would have taken less fuel, because if it was a stable position, there would be rocks and debris and things there that could damage it. So this particular position, it's like sitting on the top of the hilltop. You're stable as long as you're on the top, and when you move off to the side, boom, you're going to accelerate down. And so what they do is they use a little bit of fuel to jigger the James Webb at the top of the mountain and keep it in this metastable position. Because what happens is that, okay, the Earth's going around the sun up to the left. Well, when James Webb is on this side, the Earth is slowing it down. And when James Webb is on the trailing side of Earth's orbit, the Earth acts to pull it along. And that's what creates this metastable position for its orbit. Because only by being this far away from everything with the sun shield can you get the detectors cold enough to be able to do the science that this is going to do. Because it operates at, it's easier for me to talk in degrees Kelvin, which is like, I believe, minus 273 degrees centigrade, which is round numbers, 400 and minus 480 degrees Fahrenheit. 7 degrees Kelvin is 7 degrees above absolute zero. The background of the universe has a temperature of about 2.7 degrees Kelvin.
So
Yeah. Bruce,
how long does it take electronic measurement to get to it on a change?
okay, how long does it take? Well, let's see. In round, I don't know is the right answer, but it's basically 1 million miles away. And at a quarter of 1 million miles per second is the speed of light. It would take about 4 seconds. Now, double check that. I'm not going to swear that all those numbers are right. This is off the top of my head. Yeah.
So the detector's not cooled or anything, it's just, like, how do they keep it at 7?
No, there is cryogenic cooling of the detectors.
Oh,
So that's one of the things that they do to keep it down at that level. But when they built James Webb, they had so many things that could go wrong. And when I looked at when I was watching Nova last night, which I thought was really a good program if you have it recorded on James Webb, they said that there were 344 single point failures, meaning that if any one of those had failed, James Webb would have failed. And so one of the things they did is a tremendous amount of testing in order before they ever launched it. And one of the tests they did, and this was somewhat embarrassing for NASA, was a shake test. They took it to NASA. They took it to the Houston Space Center. I think is that Goddard in Houston? Anyway, they took it to the Houston Space Center and shook it, and nuts and bolts came loose. It set them back a couple of years. But the good news is they shook it before they launched it, and they launched it on an Ariane 5 rocket out of, I think it was French Guiana. And because it was one of the most reliable rockets, and that center is from the European Space Agency, because this wasn't just a US project. It involved Canada, the US, and the European Space Agency. Yes, John?
Materials are the mirrors made out of, please?
Okay, the mirrors themselves are made out of beryllium, because beryllium is very toxic, very hard to work with, but has some very nice cryogenic properties in terms of the way it expands and contracts. Because when they built James Webb, where did they build it? Here on Earth, at room temperature. And when they got it out into space, what temperature did they want it to run at? 7 degrees Kelvin. So the thermal shock and expansion and contraction that they had to take into consideration is just mind-blowing. And so the mirrors are made out of beryllium and are coated with a gold layer that I think is 10 atoms thick, if I remember correctly. It's very thin because gold is an excellent reflector of the infrared, and that's why they chose gold. All right.
Earth and the Webb, by this diagram, they're parallel to each other in orbit around the sun.
Correct.
Does it always stay that way?
Concentric circles. Think of them as concentric circles.
Would the Webb get ahead of the Earth and have full exposure to the middle of the sun?
Yes, and that's it. You wouldn't want it sitting in the shadow of the Earth because it needs the solar input for the solar cells to be able to run all the electronics. So that's one of the reasons why they depend on it. And I should say, this drawing is absolutely not to scale. The Webb orbit is probably a dot on this scale, and the sun should be probably somewhere over by Meridian Avenue. So you gotta take it with a little bit of a grain of salt. But I think it gets the point across about the orbit. So the math, the engineering, and the science that went into bringing this about is absolutely incredible. Any other questions? All right, thank you.